In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself, Pranav, is here to deliver today's presentation, Power Transformer Part 12. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with types of transformers. Based on the type of construction and having difference in the core and winding placement, the transformers are classified into two categories. One, coat type, and number two is the shell type. The key difference between the two types is that in coat type transformer, the winding encircles the core, whereas in shell type transformer, the core encircles the winding. See the diagram. In three-phase coat type transformer, the magnetic core consists of 3 limbs and 2 earths, whereas in shell type transformer, there are 5 limbs and 2 earths. In single phase coat type transformer, the magnetic core consists of 2 limbs and 2 earths, whereas in shell type transformer, there are 3 limbs and 2 earths. Detailed discussions in later stage. See the diagrams. And please observe the magnetic lines of flux for coat type construction and for shell type construction. Core configuration. Transformer core is basically a perfect formation of magnetic circuit and is designed to provide a path for the magnetic field to flow around, which is necessary for induction of the voltage between the two windings. The core is configured with their sheets, thin sheets of high-grade steel called laminations, which are electrically separated by a thin coating of insulating material. Depending on the transformer rating as related to cost factor, the core steel laminations are therefore be comprised of hot or cold rolled grain oriented or non-grain oriented type, and of thickness ranges from 0.23 millimeter to 0.36 millimeter. The core section would have been of circular or in rectangular shape. Circular cores are commonly referred to as cruciform construction and usually preferred for constructing higher rating of transformers. For lower rating transformer, it is much preferred to construct with rectangular shape core. The laminated steel sheets are then to be stacked for forming a composite core. The core is always be a source of heat in the transformer, and its configuration should be made in such a way that the heat as generated by the core must have to be adequately dissipated. While the core steel and insulating coating would have been capable of withstanding higher temperatures, but at the same time, it is obvious that the heat always become in contact with the insulating materials, which have some limited temperature capabilities as corresponds to their temperature class. In larger units, where the core is higher in size, having provision of cooling ducts within the core assembly may become much necessary for additional convective surface area, and a section of core laminations may also to be split to limit the localized losses. The core assembly is held together tightly by the top and bottom yoke clamps, which must be well insulated at their contact faces from the core steel. Yoke clamping studs are also be well insulated by paper-based laminate tubes. The core steel is a highly permeable material and also behaves as an effective conductor. But the core itself is not intended as a current carrying path, but only helps to provide a desirable low reluctance flux path. However, at time when the transformer is energized or the transformer is carrying load, the core may have to acquire some potential through capacitive coupling with the innermost winding, that is LV winding, resulting in partial discharges that may damage the transformer. To provide a low reluctance path of these induced potential of the core is solidly connected to earth in one point only. Through the core assembly is insulated from the grounded mechanical structures that hold it together, but the core assembly is grounded to a single point in order to dissipate electrostatic charges as produced in it. The larger core assemblies of higher capacity transformer, which have multiple core sections isolated from one another by cooling ducts, may implement core jumpers to bond the sections of the core together, and a single lead to solidly connect the bonded group to earth. Again, I repeat, the larger core assemblies of higher capacity transformer which have multiple core sections isolated from one another by cooling ducts may implement core jumpers to bond the sections of the core together, and a single lead to solidly connected to the bonded group to earth. The core earthing location is typically a single point only which should be readily accessible inside the tank, but the earthing strip can also be taken through a bushing on the tank wall or on the top cover of the better external access. However, during inspection and testing of core grounding arrangement, the earthing strip should have to be made open beforehand. Occurrence of multiple core grounds has become evident while the core is inadvertently making contact with internal mechanical structures, and for which there would have been a possible chance to provide a closed loop path for circulating currents induced by the main flux, as well as a leakage flux causing overheating in the core steel. Earthing of power transformer core assembly is of much importance for better prospect of the transformer's insulation system. Power transformer core assembly is thus to be constructed with a stack of laminated sheets of grain-oriented silicon steel, which have a very thin coating of varnish or enamel on them, so that the sheets are magnetically coupled but electrically separated. The core assembly has to be designed in perspective of providing a low reluctance path so as to have a smooth flow of magnetic flux. The windings as configured around the core assembly with the low voltage winding wound against the core and the high voltage winding then wound over the low voltage winding. Such type of winding configuration and placement against the core has intended to reduce the dielectric stress between the low voltage and high voltage windings and also between windings and core. But at the same time, the core would have been subjected to have an environment of constant induction of high potentials causing partial discharges, which may ultimately tend to damage the transformer. To divert these voltages safely to ground, power transformers are usually designed with single point solid earthing from the core of the transformer to the tank or earth or ground. This core grounding arrangement has also made to provide a low resistance path to ground if there is a short circuit between the winding and the core, allowing protective relaying to detect it. The core ground may be brought out to as a separate strip and connected with external bushing or may be connected internally. Conceptual aspect regarding selection of ferromagnetic core material. One of the most relevant criteria for the selection of transformer core is that the ferromagnetic core material as used must not be saturated during normal operation mode of the respective transformer. Performance of a transformer mainly depends upon the efficient flux linkages between the primary and secondary, and sometimes also tertiary windings, and the corresponding transformer voltages must have to depend upon the total magnetizing flux flows through the core steel. Total magnetizing flux through core is quite equivalent to the product of flux density and cross-sectional area of the core. During transformer core design, the flux density of a core can be controlled by adjusting the cross-sectional area of the core. Maximum flux density of core steel is normally to be designed as close to the knee of the saturation curve as practicable, and also to be made suggestive for required overexcitations and tolerances that exist due to subjective selection of materials and core manufacturing processes. Normally, any sort of unfavorable stress as induced on the electromagnetic steel has to create a harmful effect, by causing a degradation of magnetic properties. It's a vital one. Any sort of unfavorable stress as induced on the electromagnetic steel has to create a harmful effect by causing a degradation of magnetic properties. Such grain-oriented materials are also susceptible to impaired performance due to sudden impact of bending and blanking of the cutting edges. Highly stressed metal area usually has the extremely low permeability with having of abruptly high hysteresis loss than that of the unstressed metal area. Again, I repeat, highly stressed metal area usually has the extremely low permeability with having of abruptly high hysteresis loss than that of the unstressed metal area. When the formation of core is from stacked laminations, which are consequently sheared from fully annealed sheet or annealed material, then it is an usual practice to have the sheared laminations a stress relief annealing before stacking. To keep the transformer core dimensions smaller in size, it is quite desirable to select electrical steel of a very high operating flux density. To maintain best available magnetic properties as well as to have limit on both the core loss and exciting current, core formation with grain-oriented silicon steel laminations must be designed in such a way that the flow of magnetic flux path is primarily be in the direction as same as the rolling direction of the steel sheet. In case of power transformers, the selection of core flux density is considered typically between 1.3 Tesla to 1.8 Tesla as corresponds to the saturation point for magnetic steel being around 2.03 Tesla to 2.05 Tesla. While designing stacked magnetic cores for transformers, maximum permissible core loss is usually be one of the most important considerations during selection of the core material. It is as because that the core loss is the electrical power which is exposed in the form of heat within the core of electrical equipment when those cores are subjected to alternating magnetizing force or time varying voltage. Cold rolled grain oriented silicon steel is now universally accepted material for manufacturing power transformer core. By a process of rolling and annealing, alloys of suitable composition of electrical steel can be produced with a metallic crystal structure in which the grains are too aligned that the existing magnetic properties has become strongly oriented in the direction of rolling. Silicon is a much effective primary alloying element in electrical steels other than any element as because the volume resistivity of the steel that has been enhanced by the addition of silicon. The eddy current component of core loss will thereby also be reduced with the increase of the volume resistivity of the steel. Again, I repeat, the eddy current component of core loss will thereby also be reduced with the increase of the volume resistivity of the steel. Aluminum and manganese are the other main alloying elements added to electrical steel, which are favorably affect grain structure of the steel, thereby contributing to the lowering of the hysteresis component of the core loss. The eddy current component of core loss will generally vary with silicon content, and with the increase of silicon that will exhibit an improved core loss grade, but resulting in lowering of high induction permeability. However, the coal loss and magnetic permeability both would have to vary depending on direction of flow of magnetic flux relative to the direction in which the metal sheet was rolled. Usually, grain-oriented iron silicon alloys will have to contain approximately 3 to 3.5% silicon. If the percentage of silicon content is of much lower side, then the eddy current component of coal loss at the desired thickness of steel sheet will be too high. Or otherwise, if the percentage of silicon content is of higher side, then level of saturation density has also been reduced. Therefore, higher exciting current is required at high flux density, and that has to limit the operating parameters. Cold rolled grain oriented silicon steel as core material has low specific iron loss, but it is rather susceptible to increase loss while the flux flow in direction other than the grain orientation. While subject to operate under time varying electrical phenomenon, the eddy current component of coal loss of electrical steel has also been influenced by its thickness. Most of the cores, it has been exhibited that the eddy current component of coal loss has to vary approximately as the square of the thickness of electromagnetic materials. Most of the cases, it has been exhibited that the eddy current component of coal loss has to vary approximately as the square of the thickness of electromagnetic materials. Both the surfaces of the grain-oriented sheet are provided with an insulating of oxide coating. Available insulating materials which are capable of withstanding relatively high temperatures have permitted to restrict the overall thickness of flat rolled ferromagnetic material. Usually, available electrical grade steel sheet of 0.28 millimeter thickness with insulation coating that has approximately come to 0.96 millimeter. However, designers have a choice of core materials of required thickness, types of treatment, degrees of grain orientation, etc., so that they can obtain the necessary properties for a given design and fabricating procedure, and can produce the desired and product at minimum cost. The magnetic properties of the grain-oriented silicon steels are much more sensitive to mechanical stress, as because the strained metal has distorted its atomic structure, which consequently affects all the magnetization characteristics of the material. Constructional features of coat type transformer. In actual construction of coat type transformer, in figure 41, half of the primary and half of the secondary winding are placed one over the other concentrically on each limb instead of primary on one limb and the secondary on the other. As the primary and secondary windings are interleaved, so most of the magnetic lines of force go through simultaneously both the primary and secondary windings, resulting a strong in-magnetic coupling between the two limbs. Practically, with this type of transformer construction, a minor percentage of the magnetic lines of force will flow outside of the core, causing a low value of leakage flux in the system. The coils used for this transformer are four-wound and are cylindrical type. The cylindrical coils will have different layers and each layer will be insulated from other. LV windings are placed adjacent to core surface as it is easiest to insulate. The effective core area of the transformer can be reduced with the use of best available laminations and insulation. See the diagram. Insulation layer is provided between core and LV coil and also between LV coil and HV coil. The LV winding is usually be positioned nearest to the core surface unless the transformer has a tertiary winding which would normally be of similar or lower voltage, and in this case the tertiary winding will occupy this position. Basic concept of technical reasons. Basic concept and technical reasons. Cross-section area of HV winding conductor is less as compared to conductor of LV winding, and for transferring the same power from primary to secondary, the voltage is stepped down at the secondary end. As a result, the current in secondary will therefore be increased in the same proportion to the reduction of the secondary voltage. Since LV winding is usually be of lower voltage, hence this can easily be insulated from the earth core, as because the core which is at ground potential. Due to have a low value of current flowing in HV winding, so tap changers, if required, are most likely to be placed on the HV winding as there is less wear on the tap changer contacts. Because the cross section of connecting lead is less, so it is also become easier to accommodate the connections of the HV winding to the tap changer. In that case, LV winding will only have the leads at the start and finish, which can be easily accommodated at the top and bottom of the core limb. The LV winding is normally wound on a robust tube of insulation material. This material has high mechanical strength and is capable of withstanding the high current loading that it experiences during the winding of the large copper section coils used for the LV windings. Leakage reactance that has to depend on distance between core and HV winding. HV winding, if it is placed farthest to the core, then the leakage reactance of the primary is low. The low leakage reactance means most of the flux produced in the primary winding gets linked to the secondary. The inrush current of the transformer gets reduced. Furthermore, the voltage regulation of the transformer is therefore be improved. See the diagram, three-phase power transformer code type. The assembly of the laminations can be done with the shape of E and I. As the transformer core is constructed from thin sheets, which is always be subjected to an electrical impulse, so length, width, and conductivity coefficients of the laminated steel sheets should have to be selected much more judiciously. Particularly for larger power transformer core, very thin electrically insulated laminated steel sheets are used to reduce losses by restricting the flow path of eddy currents. But it is obvious that the thickness of the lamination is often determined by the cost of manufacturing thin lamination against the losses incurred. As per the necessary dimensions of the power transformer core, the laminations are cut in size and properly stacked, which is then to be clamped rigidly and permanently attached to the bolt. Laminations are usually stacked alternately to each other, which cause to happen an overlapping joint with more lamination pairs being added to make the core thickness as per exact requirement. See the core construction type, E and I. The alternate stacking process of the laminations also has to imply reduced flux leakage and iron losses in the transformer core assembly. Clamping arrangement is usually preferred for perfect placement of laminations into their own respective places, as because bolting arrangement may have to interrupt the flow of flux. In a bolted core, yoke construction has to ensure rigidity of the core. But as the holes are punched in the yoke lamination, so some distortion of flux at the position of holes is become inevitable, resulting an increase in core loss. Bolts may also have a tendency to loosen when subjected to the vibrations. So instead of bolted core yoke construction, manufacturers are using some special clamping arrangement, which is made of fiberglass or stainless steel bands. Adapting such type of yoke construction has ultimately intended to better utilization of core material and reduction in core loss. However, some provision of small guiding holes would have to be imposed so as to facilitate the placement of laminations and core building processes. In order to make a better bonding of laminations, suitable epoxy resin is applied at the edges of yoke laminations, which may also attribute in reduction of noise level. Just to provide a maximum core area for a given core diameter, larger number of steps are usually preferred for the construction of the core limbs. Whereas yokes may have to construct with the lesser number of steps, and that has to provide for better axial support to the windings. The mismatch in number of steps for making limb and yoke may also lead to some extra losses at the corner joints. As the compactness is a major requirement to this clamping arrangement, must have to remain tight, and any occurrence of sudden increase in noise or vibration of the transformer that may indicate a possibility of loosening of core structure. Necessary insulating parts such as plyboard or yoke clamping and columns for winding support are manufactured as per requisite requirements. HV and LV windings are constructed in separate and placed on the respective core legs after the core assembly. Iron core is first enclosed by the low voltage coil and then again enclosed by the high voltage coil. Connection points are welded at each end and brought out from each winding to allow for the installation of cable or bus. Let's stop here. further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you.